So first, thanks to both committees for the opportunity to talk. So I will present this Acyclonestohedra, joint work with Karen Mantovani and Arnaud Padrol. So my goal is to explain you these two pictures. Let me start with the motivation of the construction, which are posted Acyclonestohedra. They were introduced by Galashin recently. And let me start by Acyclonestohedra and the way to understand the Acyclonestohedron. So let's start with endpoints on a line. And these points are moving continuously. Let's imagine that they move, and I want to remember when some points collide. Okay, so I have some colliding events. And okay, maybe I have 3 points at the same time which collide, and imagine that at the end I have only 1 point. Okay, so this will be my collapsing line. And in order to combinatorially remember that, I can just draw the time vertically and remember the position of the points at any time, and I get a Schroeder tree, so a tree with where each vertex has at least 2 children. So this is the combinatorics of the Acyclonestohedron. Okay, so instead of using Schroeder trees, we will use other combinatorial models. The first are pipings, and the second are tubings. So what is a piping? Well, what I will do is that I will remember all colliding events. So each time I have some points colliding, I will just draw a bubble around it, which I call a pipe. And so these pipes have the properties that they have to be either nested or disjoint. Okay. And here on the bottom, you really see the Acyclonestohedron with all possible maximal piping. So just to be sure that we're on the same page, maybe we can try to find this collapsing chain in this picture. So here you see that it will be one-dimensional because there is it's quite difficult to. There is a vertex of degree 3, so it's not. So this will be one-dimensional and correspond to this edge. Okay. Okay, so that's one way of remembering this collapsing, and the other way is these tubings. So now I do essentially the same, except instead of remembering which points collide, I remember which intervals between 2 points collide. Okay. So I will have one less point now because I have 1 point for each interval, and I remember when points collide, I remember the corresponding intervals which just collapse. Okay. So now the properties of these tubes is that they are either nested or disjoint and non-adjacent. Okay. So that's 2 different ways of thinking about it, and we'll need this second way. Okay. So now Galashin proposed to do the same on a poset. So now we start with a poset, and we look at continuous functions which are order preserving, and so that's the last function is just collides everything to a point. Okay, so that's a poset Acyclonestohedron. Well, we will remember combinatorially. We will remember that again by these pipes. So each time I have some points which collide in the poset, I will just put a pipe. So there are some configurations which are not possible. So for example, this configuration here is impossible. So if 2 and 4 collide and 2 and 3 collide, then either they collide all at the same time and I have only one pipe, or let's say 2, 4 collide first and then 3, 2 collides with 2, 4, but then the pipe containing 2, 3 should also contain 4, right? So it has to be nested or disjoint. But there are more problems. So for example, this is also impossible. So if 1, 2, 3 collide, well, at the moment when they collide, then as my functions are order preserving, 5, which is in between 1 and 3, should also collide with them at the same point. Okay, so that's also impossible. And also this one here is impossible. So here 1 is more than 5 and 4 is more than 2. So if 1 and 2 collide and 4 and 5 collide, then they should all collide at the same time. Okay, so that's a poset Acyclonestohedron. So the poset Acyclonestohedron, you can combinatorially you have a set of pipes. So the pipes are these connected subsets of your poset of size at least 2. And the piping is a collection of pipes, so that the pipes are pairwise disjoint or nested, so I cannot have this problem. But also, if I take any subset of my pipes, and I take the union of this subset and quotient my poset by this union, I should have something acyclic. So I don't want this. When I quotient by 1, 2, 3, then I have something cyclic with 5, and I also don't want this. So if I contract 1, 2, and at the same time 4, 5, then I have something cyclic. Okay. And the piping complex is the simplicial complex of all pipings of the POSET. Okay, so here are examples. So we will follow these two POSETs. So they're slightly different. So I have drawn here all possible pipes. You see that you don't have the same number of pipes, even if you have the same number of vertices and edges. Well, you see that I have a nice piping complex. It's a sphere, so it's a simplicial sphere, and actually we'll try to realize it as a simple polytope, as a dual of a simple polytope. So this would be these pictures. It's not at all obvious that there are duals of simple polytopes, and this is a result of Galashin. He proves that the P-Acyclonestohedra can all be obtained by truncations of the order polytope of P. Okay, but truncations is something difficult to do. So you have to find some parameters, some epsilons. It's complicated to give it to a computer. So he immediately asked in his paper to find nice realizations, and there are two independent realizations. So Andrew Sack presented a realization last year at FPSAC, and I want to show you different technique to obtain this thing. So how does it work? I promised you that we not only will use pipes, but we'll also use tubings. Okay, so now I want to represent these pipings as tubings. So instead of remembering which are the points which collide together, I will remember which are the cover relations of the POSET which collide. Okay. So for this, what I do is that I start from my POSET, and I construct the line graph of this POSET. So I have one vertex for each cover relation, and one click for each vertex here. Okay. And now, so what I will do, I just translate it from top to bottom. Each time I had a collision, so for example here I had a collision between C and D, so I was colliding edge 4. I had a tube here around 4. Okay, so I just made the translation. And now let's look at what we have below. We have what is called a tubing, but not all possible tubing, just some of them. Okay, so we'll see that these tubings are certain part of what is called the graph associahedron. But you can look at what it looks like on the graph associahedron. So here I represented a polytope where you have all possible tubings, and in green I coded the one which are tubings corresponding to pipes, and in red the ones which are forbidden. Okay, so when we saw this picture, we were happy with Karen and Arnaud, because as geometer, we realized that we could really select the acyclic part, the green part, by just a section. Okay, and that will be the construction. Okay, so I will show you that we can construct the P-Acyclonestohedron as a section of the graph associahedron of the line graph of P, a certain graph associahedron, sorry, a certain realization of the graph associahedron and a certain section. Okay, so my goal is to show you this, but I want to show it in a more general context. And for this, I need Nestohedra and oriented matrices. So let me start with Nestohedra. So I will have a ground set S, and I consider a building set on S, which is a collection of non-empty subsets of S, which contain all singletons and have the properties that if I have two subset B and B prime which intersect, they should also be in my set. And I will denote by kappa of B the connected components of B. Okay, and when you have a building set, you can construct what is called the nested complex of this building set. So it's a simplicial complex of nested sets, and a nested set is just a subset of B, where for some reason we remove the connected component. And you want that any two elements in this set are either nested or disjoint. And if you take k pairwise disjoint elements in this nested set, then you want the union not to be in B. Okay? And it was proved by Feichner, Stumpfels, and Postnikov that nested complex is isomorphic to the boundary complex of the polar of a polytope, which is called the Nestohedron, and it's very simple to obtain it. It's just the Minkowski sum of the faces of the standard simplex corresponding to this the elements in B. Okay, so since we're only interested in the combinatorics of this Minkowski sum, we can actually put some coefficients in front, and it will be useful for us. You can just, if you put a positive coefficient in front of the Minkowski sum, and you don't change the combinatorics, and it will be important for us. Okay, so here are examples of two Nestohedra. So on the bottom, you see the building sets. So I did not represent the singletons. All singletons are here, and here I just represented all possible building sets. And then on the computer, what I did is that I just computed the Minkowski sum of the corresponding faces of the standard simplex, and I obtained these polytopes, and you see that the vertices correspond, or let's say the faces, they correspond to all possible nested sets on these building sets. And there is a particular case which will be important for us, which is a graphical case. So you start from a graph, an undirected graph G, and you consider what are called the tubes of this graph, so the subsets of vertices which induce connected subgraph. So it is a building set, it contains the singletons, and if you take two connected subgraphs which intersect, their union is also a connected subgraph. And out of this, you can construct the graphical nested set and the graphical nestohedron, which is also called the graph associahedron, and was constructed by Karen de Vados previously. Okay, so that's all I needed for nestohedra. Now I need oriented matroids. So I will have to cheat a little bit and tell you what is an oriented matroid of a vector configuration. So I start from a set of vectors, a collection of vectors indexed by my ground set S. So there are vectors in RD. And I will be interested in the linear dependencies of these vectors. So all possible ways to write 0 as a linear combination of these vectors. And the linear evaluations of these vectors, so all possible evaluations of a linear function on these vectors. Okay, and these two sets will be important for us, and then we will construct what is called the oriented matroid of this vector configuration, which is a combinatorial data, which encodes combinatorially the linear dependencies and the linear evaluations on A. So for this, what we'll do, first thing is that if I have a, if I have a tuple, I can, out of this tuple, I can, a tuple of reals, I will associate a combinatorial data, which is this, I remember which of the entries are negative, which ones are positive, and which are 0. So I call that the signature of this tuple. And now, the oriented matroids of A is, you can give any of these four sets, so the set of vectors, which are the signatures of the linear dependencies of A, or covectors, which are the signature of the linear evaluations of A, or circuits or co-circuits, which are the support minimal vectors or covectors. Okay, so this, you can remember any of these four sets. It would be what we call the oriented matroids of A. So let me give you an example. So I start from these 6 vectors in dimension 4, and this vector configuration, they have 13. It has 30. So the naming is very bad, but it has 13 vectors. So signatures of linear dependencies, 153 covectors, 6 circuits, and 14 co-circuits. Let me just go through one circuit and one co-circuit. So for example, this circuit 1645, it corresponds to the fact that if you look at vector 1 plus vector 6, it's equal to vector 4 plus vector 5. So you have a linear dependence which is 1, 0, 0, minus 1, minus 1, 1. And this is the sign vector of this linear dependence. And let's look at a co-circuit. So this co-circuit 1, 2, 6, it means that there is a linear function which is positive on 1, 2, negative on 6, and 0 everywhere else. So let's take the last coordinate, minus first, minus second, minus third. And you get 1, 1, 0, 0, 0, and minus 1. Okay. Okay, so now I explained to you what is an oriented matroid of a vector configuration, and I will explain to you what is an oriented matroid. Well, an oriented matroid is just a combinatorial data, which you can take any of these four sets. So we call them the vectors, the covectors, the circuits, and the co-circuits of the matroid, and they have to behave exactly as those of a vector configuration. Okay? So you don't want to see the axioms, but you have to think of it as a combinatorial abstraction of linear dependencies and linear evaluations. Okay? I need to tell you two things on oriented matroids that we'll understand in the next slide on the graphical case. So the first thing is that there is a natural notion of restriction and contractions in oriented matroids that you probably know on classical matroids. And the second is that it's important for me to know what is an acyclic oriented matroid. It's an oriented matroid where there is no positive circuit. So before it meant I have no linear dependence with only positive signs. Positive and zero signs. Okay, so let me do the graphical example, which will be important for us. So start from a directed graph, whose vertices I will denote by V, and the set of arcs is S. Out of this graph, I can construct the incidence configuration of the graph, so the set of vectors EI minus EJ for all arcs IJ. And the graphical oriented matroid is the oriented matroid of this incidence configuration. So if you think about it, what are the linear dependencies in this incidence configuration? Well, a way to get the linear dependencies, you just take a cycle, choose an arbitrary orientation on your cycle, and now each time you have an arc which is clockwise, you just put a 1, and each time you have an arc which is counterclockwise, you put a -1. Okay, this gives you a linear dependence. These are the circuits. These are the minimal ones if you start from a simple cycle. And to get a covector, so a linear evaluation, what you can do is you pick a cut in your graph. So you take some source vertices and the complements, which are the sink vertices, and look at all edges which go from the source to the sink. You put a 1, and for all edges which go from the sink to the source, you put a -1. Okay, and this would give you an evaluation. Okay, so for this graphical case, we can understand here the restriction and the contraction. So the restriction, you pick a subset of the arcs, and you just look at the graph where you just keep these arcs. Okay, and it gives you a new oriented matroid, and this is a restriction that I did not really explain before. And for the contraction, you pick a set of arcs and you just contract this set of arcs, and it gives you a new graph whose oriented matroid is a contraction. And here for graphical oriented matroids, the acyclicity is really the acyclicity of the graph, so you have no directed cycle. Okay, so now we are ready, and I can tell you what is an acyclonestohedron. So we start with a combinatorial data, which we call oriented building set. So it's a pair where you have a building set on the ground set S, and an oriented matroid on the same ground set S, and they have to be compatible in the sense that if you take any circuit in your oriented matroid, then the support of the circuit should be a block of your building set. Okay? Why not? Okay. Then when you have that, then you can look at the nested sets on B, and we'll select the one which are acyclic in a certain sense, and this sense is the following. We want that, so a nested set N is acyclic if for any subset of N, if I contract my oriented matroid with respect to the union of N prime, then what I get is an acyclic oriented matroid. Okay? And the acyclic nested complex is a simplicial complex of acyclic nested sets. Well, this condition is clearly closed, so it is a simplicial complex. Okay, and we have two main theorems. So the first is that if you take any oriented building set, the acyclic nested complex is the phase lattice of an oriented matroid, which you can obtain by stellar subdivision of the matroid M. I will not insist too much on this one. And the second theorem is that if you start from an oriented matroid, which is realizable, so if you start from an oriented building set where the oriented matroid is an oriented matroid of a vector configuration, then the acyclic nested complex is a boundary complex of the polar of a polytope, which we call the acyclonestohedron, and it is defined as a section of the nestohedron corresponding to this building set with the evaluation space of A. Okay? So the nestohedron here is the technicality. The nestohedron, I cannot take just the sum of the faces of the standard simplex. I have to put a coefficient in front, and the size of the coefficient depends on how long you want the proof. So if you want a small coefficient, you will pay a lot. If you want a short proof, then you will have big coefficients. Okay, so let's do the graphical case, first application. So I start from a directed graph, vertices V and arcs S, and I call graphical oriented building set the building set where the oriented building set where the oriented matroid is just the oriented matroid of this directed graph. Okay, and the building set is a graphical building set of the line graph of the directed graph. Okay. So let's just think 2 minutes. So first thing is that these two things, they are indeed, it's a building set on, so the ground set here is a set of arcs, and here the ground set of B of LD is a set of vertices of LD, but this is also the set of arcs of D. So they are at least on the same ground set. And now if you take a circuit on D, then if you think 2 minutes, it will give you a cycle in LD, so in particular it will be connected in LD, so it will be indeed in the building set. Okay, and what we observed is that the acyclic nested complex of this graphical-oriented building set is a piping complex of the transitive closure of D. Okay? In particular, we obtained what I promised before, is that the piping complex is a boundary complex of the polar of the graphical Acyclonestohedron, which you can obtain as a section of the graph associahedron of a certain graph associahedron of the line graph of P by what is here is just a evaluation space of D. Okay, so I think I still have a little bit of time to tell you what we actually do. So we realized later that we were doing something more interesting. And for this, I have to tell you what are lattice nested complexes. So I think we are less familiar in this community with the initial definition of lattice nested complexes. So, so it was defined by Fechner and Kozlov. They actually start from a mid-semilattice, but let's start from a lattice in our case. So I have a lattice L, and what we call an L building set is a subset of L with this weird property. So each time you take an element X in L, you can look at what are the maximal elements of B which are below X. Okay? And you want that the interval below X is the Cartesian product of the intervals below these maximal elements below X. Okay? So it's a bit difficult to pass. Let me try to pass it on an example here, which is just a Boolean case. So I look at this Boolean lattice, and here I decided to take in B the elements which are circled. And now if I look at 1, 2, 3, 4, the maximal elements below 1, 2, 3, 4 are 1, 2, and 3, 4. And indeed, the Boolean lattice below 1, 2, 3, 4 is a product of the Boolean lattice below 1, 2 by the Boolean lattice below 3, 4. Okay? But now if I would have started from this set, so 1, 2, 3, and 3, 4, and look at 1, 2, 3, 4, then the Boolean lattice below 1, 2, 3, 4 is not the product of the red and the blue. So if I take 1, 2, 3, and 3, 4, I also have to take 1, 2, 3, 4, and this is the usual definitions that we know for Boolean building sets. Okay, so this is the notion of lattice building sets. So as I just said, if L is a Boolean lattice, then the Boolean building set are just the classical building sets. And now out of this, when you have a lattice building set, you can construct the corresponding lattice nested complex. So a lattice nested set on B is a subset of B, so that any K, if you take pairizing comparable elements, B1, Bk, then the join of B1, Bk should not belong to B. Okay, so if you translate it in the Boolean lattice and the L nested sets, the Boolean nested sets are really the classical nested set that I defined before. And so the nested complex is a simplicial complex of L nested sets on B. Okay, so now I will just consider a very special lattice, which is a Las-Vernas face lattice of the oriented matroid. So the face of an oriented matroid is a subset whose complement is a positive circuit. A positive what do I want to say, covector. And the face lattice is the inclusion poset on these faces. Okay, so this is a very special lattice. And what we prove is that this, first thing that we prove is that the facial building sets that we, what do I want to say? Let me start with the definition. So if I start from an oriented building set, I can construct out of it what we call the facial building set, which just consists of the blocks of my building set here, which are also faces of the oriented matroid. So just a subset of B. And first thing that we prove is that the facial building sets are exactly the building sets over the Las-Vernas face lattice of M. And the second thing that we prove is that the acyclic nested complex that we considered before is exactly the lattice nested complex of this facial building set over this Las-Vernas face lattice. Okay? So as a corollary, what we obtain is that if you start from any oriented matroid and look at the Las-Vernas face lattice of this oriented matroid, the corresponding nested complex for any facial building set is first the face lattice of an oriented matroid that we obtain by stellar subdivisions. I did not speak too much about that during the talk. And also, if I start from an oriented matroid which is realizable, then it is a polytope, which you can obtain either by realizing the stellar subdivision polytopally or as a polar of a section of a nestohedron. Okay, so we just adapted the theorem before to this case. Okay, so Let me give you 2 more applications. The first is what we call type B Nestohedra. So you start from this vector configuration, which is a set of vertices of cross polytope. And well, you can look at the facial nested complex, the face lattice of this oriented matroid, and the corresponding facial building set will give you some interesting Acyclonestohedra. So, for example, if you take the full facial building set, what you obtain is a type B permutahedron, and you really obtain it as a section of the type A associahedron, as you expect. But you can also do more interesting things, so let me just jump. One very simple way to construct a facial building set on this spatial configuration is to put building sets on the positive part and on the negative part. And even simpler, you just put the singletons on the negative part, and what you obtain is this paper by Devados and VP Makul, which are the design Nestohedra. And the last application is, well, let's do the following. You start from a polytope. You homogenize this polytope to get an oriented matroid, and you choose an oriented building set. Okay, you get a new polytope, which is Acyclonestohedron. Now homogenize this polytope, choose another oriented building set, and you get a new polytope, which is an Acyclonestohedron. And you can keep going and keep going. What you obtain is a iterated Nestohedra. And for example, if you take each time you take the full building set, what you obtain is a permutahedra. It was considered by Castillo and Liu. They consider as a two-fold version. We have no reason to stop after 2. But you can also just pick another building set at each step. Then what you obtain, if you do it twice, you obtain what Gaifi calls Nestohedra. So that's one more application. Okay, and thank you very much.
Thank you for the talk, and perhaps there's time for one short question, if there is one. Yes.
Thank you for the talk. In the previous example, so just on the previous slides, the Nestohedra, am I correct that each polytope that you obtain is obtained as like cutting the previous one, some faces of the previous one?
Yes.
And is it always the case, whatever building set that you take, that the next polytope, so you in that process you choose one building set, which is BI. Is this correct? And then PI plus 1 will be a cut of
yes,
PI?
You have to do it in the right way, but this is what we mean by this is what we mean by realizing the stellar subdivision polytopally. So the polar of stellar subdivision is truncations, and you have to do it the right way, but this is what you are doing. Thanks for the question.
Okay, there is some opportunity to ask more questions right after during the poster session, which now happens. And because of this, I would like to thank now all the speakers of the afternoon and all the contributors to the poster session. Thank you very much.